Okay, so let's start the next unit, which is similar polygons. So, what are similar polygons? It's similar figures. The idea is same shape, different size. So we're going to assume it's different sizes. And so the idea is, so let's see. The idea is that we're looking at so all the corresponding angles are congruent, and the ratio of corresponding sides are in proportion. So that's the big change. So let's start with a similarity statement. So let's start with a similarity statement. For example, we're going to say that A, B, C, D is similar, that's the symbol for similar, to E, F, G, H. So what I'm going to do is I'm going to make a picture on the board. So let's see. Well, let's have trapezoid A, B, C, D and trapezoid E, F, G, H. Let's see. Let me just make sure. A, B, C, D. And we're going to look at E, F, G, H. Okay. Now, the idea is from the similarity statement, immediately we can see which angles are congruent. So we know that angle A is congruent to angle E. We know from the similarity statement that angle B is congruent to angle F. We know from the similarity statement that angle C is congruent to what? Angle G. And then the last is angle D is congruent to angle H. Now, the angles might be congruent, but the sides are not. This is where similarity comes in. The idea is that the ratio of corresponding sides are in proportion. Well, what's going on here? Well, we can see that the idea is that AB, so first of all, let me use colors. So AB corresponds with EF. We have BC corresponding with FG. We have CD corresponding with GH. And we have AD corresponding with EF. They correspond, not congruent, but the idea is the ratios are in proportion. AB over EF is equal to BC over FG is equal to CD over GH is equal to AD over EH. Okay? And the idea is all these ratios are in proportion. This in particular, this is known as an extended proportion. Extended proportion. The idea is that we have three or more ratios that are equal to each other. So let's see, three or more ratios that are equal. And then the idea is you're going to have all these fractions, and we start from the last lesson. If all of these fractions reduce to simplest form, then we have them, they're in proportion, and therefore that's the idea of similar polygons. Okay, a simple example. Let's start with example 1, 2 right triangles. So here's a right triangle, here's a right triangle. I'm showing you that the smaller one has sides 4, 3, and 5. I'm showing you that the bigger one has sides 8, 6, and 10. And also that all the angles are congruent. So the question is, are these right triangle, are they similar? And you say, yeah. Are they similar? Similar? And you say, yes, because all the corresponding angles are congruent. And let's compare the ratio. So what matches up with what? First of all, in triangles or any angles, I like to match up the angles by saying right single, right single. I know that 4 corresponds with 8. I know that 3 corresponds with 6 because, right double, right double. And I know that the hypotenuse corresponds with the hypotenuse. Are the ratios in proportion? Maybe. Let's check it out. So let's see. I know that 4 over 8 needs to be equal to 3 over 6, which needs to be equal to 5 over 10. Do all these simplify to the same simplest ratio? The answer is, the answer is yes. Let's see. Well, 4 over 8 is 1/2. Nice. 3 over 6 is 1/2, and 5 over 10 is 1/2. Therefore, because all the angles are congruent and all the ratios of corresponding sides are in proportion, we can say that these triangles are similar. Good. Next question. Let's move the screen over. Nice. Next question. Here's a diagram. We're going to put a trapezoid in a trapezoid. Let's put a trapezoid inside a trapezoid. And let's see what we have here. Let's see, I'm telling you, let's call this A, B, C, and D. And let's call this angle here up E, F, G. I'm telling you that A, B, C, D is similar to E, F, G, D, E, F, G, D. And let me put some lengths in here. Let's say that AD is 9. Let's say that AB is 5. Let's say that BC is 7.5. Let's say that ED is 6. EF is Y, and FG is X. And so the question is, whoops, sorry, let me stand on the side. Can you see everything? Yeah, the question is find X and Y. Well, maybe we'll put the numbers in the diagram. Let's see, AD is 9. We have AB is 5. We have BC is 7.5. We have ED is 6. And we have this is Y. And this is X. Okay, so what's going on here? Well, we know they're similar, so we know all the corresponding angles are congruent. The question is, we also know that the corresponding side, the ratio of corresponding sides is in proportion. So the first thing we're going to do is, well, what do we have any sides to match up? And you say, oh, you know what? AD matches up with ED. To go from the big to the small, the ratio is 9 to 6. So AD over ED is equal to 9 over 6. This is known as our scale factor. This is our scale factor, and this is going to help us solve the problem. So we can say, you know what? Everything is in the ratio of 9 to 6. So to find Y, we say, fine. That means AD over ED is equal to AB over EF, because we can see from the diagram here, we can see that, AD corresponds with AE. We can kind of match that up. We can say that AB corresponds to EF. So I can write 9 over 6 is equal to 5 over y. And so I have 9y equals 30. Y is equal to 30 over 9. Let's see, what is that? It's 10 over 3, about 3.3. Nice. Can we find x? Yeah, that's easy also. You say, very easy. Once again, AD over ED is equal to BC over FG. Once again, we're matching up the ratio of corresponding sides. Once again, AD matches up with ED, and BC corresponds with FG. Okay, so 9 over 6 is equal to 7.5 over x. Let's put this together. What do we have here? Let's see, we have 9x is equal to 45, because 7.5 times 6 is 45, yeah, and that means x is equal to 5. Nice, interesting. And we can find, actually we can't find the other sides because we don't know what the base is. That's not important. Good, let's move on. And then the idea with these problems, you're looking for the corresponding parts and angles. Let's take this into the real world. Let's see, let's move it over. Let's move it up. Okay, next, imagine. So here's a real world problem. For those of you who do like design artists, let's imagine that you have a poster. Let's imagine that you have it, let's say, imagine in school, we have a big wall, a big mural, and the wall it's 4 feet by 8 feet. This is the mural. And the idea is we're going to take a poster. You're going to take a poster that is 6 inches by 10 inches. So the idea is you're going to decide as a class, you're going to make a poster, and the idea is you're going to blow this up. And you're going to blow it up so it fits in on the wall. Once again, yeah, that's the idea. So I want you to think about how the best way to blow up this 6 inch by 10 inch, small poster. I want you to blow it up so it best fits in the mural, which is 4 feet by 8 feet. So I want you to think about that. So I'm going to take a step back. Okay, so what do you think? So the question is, what are the dimensions of the poster that will fill the space? Well, what do you think? So first of all, what I would do is I would turn these into inches. So this is 48 inches. And this is 96 inches. Now, I know that I have to blow this up. So let's see, let's start with the base. How about we make the base, the small base, into the large base? So what we're going to do is I'm going to take if I take the scale fragment, let's see, to go from 10 inches to 96 inches, it's like multiplying by 9.6. Well, what happens when I multiply 6 by 9.6? Let's see, 9.6 times 6, 6, 3, 57.6. Am I able to do this? No. The problem is, if I blow it up by a factor of 9.6, then the height is too large for the mural. So let's take another, so not possible to have a factor of 9.6. So let's try the other way. So let's go from, that's no. So that's no, okay? Let's try to go from 6 to 48. So let's do a scale. So let's go from 6 to 48 and have a scale factor of 8, right? So if 6 goes to 48, then where's 10 going? To x, right? So we have 6x equals 48 times 10. X is equal to 48 times 10 over 6, which is 80 inches. Is that okay? And you say, yeah, yes, that we can do. So the largest poster we can make is yes. So the idea is with a scale factor, a scale factor of 8, right? Because we decided to go from the 6 to the 48. Yeah, of 8. Our poster will be enlarged to, let's see, 6 times 8 by 10 by times 8, which is 48 feet. Yeah, 48 inches by 80 inches. Will it fit in the space? Yes, it'll fit. And that's the idea of proportions. That's the idea. You want to blow things up by the same number. So once again, I could have multiplied both of these by 9.6, but then the height would have come above the mural. My other option was to multiply both things by 8. That would have kept it inside. Looks something like this, maybe, but here's kind of like this. So that's what this got blown up to this, with a little space to spare. That's the idea. Nice. The last thing I want to talk about is something called scale drawings. Let's see. So you see this you'll see that, like, move the screen over. You will see this with, let's just say some notes. A scale drawing. The idea is that all lengths are proportional to the actual corresponding lengths. You're going to see this on maps. You're going to see it on architects' plans. So for example, you're going to see a drawing of a house that isn't the house, but the way that the architects draw it, it correctly maps to the actual building. If you actually took the picture and enlarged it to the actual house, it would actually be that house. So the idea is the scale is the ratio. The scale is the ratio. And the idea is, you recall this from maps, that a scale looks something like this. We're going to say like 1 centimeter is equal to 200 meters. We might see this on an architect's plan. Maybe you did something like in middle school, you had to like design your room and you had a picture. It wasn't the room, or most specifically, what you know is a map. So you look at a map of Nigeria, you see the whole map. That isn't the whole country, but it represents. And if you go to Google Maps and you look at the lower right-hand corner, you can see an actual little thing that actually shows the distance, like probably like an inch, a centimeter, and it says like 500 meters. So let's say a scale drawing, example 1. A scale drawing. Scale drawing is 7 centimeters. How long is the actual object? How long is the actual object? And you say, okay, no big deal, because I know that 1 centimeter represents 200 meters. So in your head, 7 represents 1400. That's right. Let's get an equation down. So the scale is the ratio. So it's 1 centimeter is to 200 meters, as 7 centimeters is to x meters. That's once again, these two ratios are in proportion. 1 corresponds to 200, 7 corresponds to, 1 centimeter corresponds to a reality of 200, 7 centimeters corresponds to a reality of x. Cross multiply. Leave off the units. That's not important. I mean, it is important, but we know the answer is x meters. So we have 1x equals 7 times 200. So the x equals 1400 meters. It doesn't necessarily have to be bigger. You could be talking about like the length of atoms or cells or something like that, where it's like on your paper, 1 inch represents like a trillionth of an inch or something like that. Let's try the last problem. I'm going to erase this. The last example, let's keep the scale. Oh no, let's not keep the scale. So this is a two-part question. Let's see. The Space Needle. Let's see. The Space Needle. How are you doing for time? Good. The Space Needle in Seattle is 605 feet tall. Okay. And the scale, you decide the scale, is 1 inch is equal to 50 feet. My question is, can you draw the scale on an 8.5 by 11-inch piece of paper, like A4 paper? So can you draw this on A4 paper? And A4 paper in the United States is 8.5 by 11 inches. Can you draw it on the piece of paper? So you say, okay, I just need to get my height. The maximum height here needs to be at least 11. You know what I'm saying? Like, here's my paper. I need this. Here's the picture. I need it on the paper. This needs to be 11. So let's see. We know that 1 is to 50 as x is to 605. Let me put this on pause while I get my calculator. Okay, we're back. So here's our ratio. 1 to 50 is the picture to the actual thing. Maybe I should put like inches here and feet, inches to feet. Once again, I'm not saying that this is equal to each other. This is just the scale. Remember that this is a scale. So in this case, 50 feet is being shrunk down to an inch. The question is, what is 605 getting shrunk down into? Cross multiply. Let's see, 50x equals 605 feet. X equals 605 divided by 50. Hey Siri, 605 divided by 50.
605 divided by 50 is 12.1.
Okay, that's a problem. It's not going to fit on this paper. Maybe we should change the scale. But the idea is you change the scale. I'm going to shut the video off now, but I want you to think about what we should change the scale to fit it on the paper, and that's basically it.